Quantum Transfer Learning for Diagnosis of Diabetic Retinopathy by Dr. Sridevi S., Dr. Kanimozi T., K. Somashekar Reddy, Dori Shehwar, and Sayantan Bhattacharjee. In order to detect retinal problems, OCT or optical coherence tomography is a widely used technique. Some of the limitations of the OCT have been mentioned here, which include the use of light waves, which limits its field of penetration, and the dependency of the quality of the image on the operator of the machine. Here, we are using quantum transfer technique in order to deal with a huge amount of data set. Hence, an idea is proposed to do classification using quantum transfer learning using the existing data set obtained from the OCT. Coming to the abstract, computer-aided diagnosis has helped to solve retinal diseases. This project is mainly focused on classification of the image acquired from computer-aided programs. It does classification of images between normal, CNV, DME, and drusen. But due to the limitations of OCT, it does two-class classification only, that is, normal and CNV, normal and DME, and normal and drusen. The algorithm used for the transfer learning is ResNet 18, and the features extracted from it is further transferred to quantum circuit, which does the classification. The quantum computing has helped to do classification with less amount of data, which has helped to reduce the storage space and increase in the speed. The objective of this project is to train the model on transfer learning algorithms and then use quantum circuit to classify the images in order to detect retinal diseases. The model used for the project is ResNet 18 and quantum computation. Let's turn now to introduction. The stats shows that among the 128.5 million people affected from diabetic retinopathy, 33.25 million people fall under vision-threatening diabetic retinopathy. This problem has led us to find novel solution in order to solve the issue. After some research, we found that quantum transfer learning can be used to classify the images using the OCT images.
So these are the major papers which we have referred for designing this model. The approach and accuracy of each paper has been discussed here. Our dataset contains 4 classes of images: CNV, DME, drusen, and normal. The dataset contains 84,495 images in JPEG format. The dataset is organized into 3 folders: train, test, and validation, and contains subfolders for each image category: normal, CNV, DME, and drusen. Here is the overall block diagram representing the overall proposed model in the paper. Initially, the dataset size is modified such that it contains 1000 images in total, containing 250 images in each 4 classes, namely normal, CNV, DME, and drusen. Since the quantum transfer learning model is meant mainly for binary classification, the datasets are divided into 3 databases, that is, normal and CNV, normal and drusen, and normal and DME. Each folder consists of 400 images for training and 100 images for testing. The images are then pre-processed by resizing them into 256 cross 256 dimensions, then normalizing them in order to remove the skewness, and finally converting them into grayscale images. The dataset is then passed on to the transferred learning model. Transfer learning is a research problem in machine learning that focuses on storing knowledge gained while solving one problem and applying it to a different but related problem. The model that we have used here for transfer learning is ResNet 18. ResNet 18 is a convolutional neural network that is 18 layers deep. We can load a pre-trained version of the network trained on more than a million images from the ImageNet database. The purpose of using transferred learning is used to extract features that are learned by the model. These features are then down converted from a size of 512 to 4 using linear transformation layer. The 4-dimension feature set is then passed through the VQC, that is, the variational quantum circuit. The VQC is a type of neural network realized as per the quantum requirement with a fixed number of quantum gates and is made up of sections of embedding layer, variational layer, and the measurement layer. The embedding layer consists of Hadamard gates, which is used to introduce encode the input qubits. The variational layer consists of rotational gates and CNOT gates, which is used for the main calculation, and the measurement layer consists of poly Z gates, which is used to measure the Z operator of the qubit and convert qubits back to classical bits, resulting in a vector. This vector is again down converted into a vector size of 2 using linear layer, which is used for the final classification.
The proposed research and its experimental findings were observed on the Google Colab platform using the Pennylen and the PyTorch library. The dataset size used for this overall experiment was 1000 and the optimizer used is Adam optimizer. So the model used for transfer learning is ResNet 18 and the number of epochs for which the overall model is run is 20. In this proposed work, we utilize small individual segregated data sets DB1, DB2, DB3 to analyze the performance of variational quantum circuit based quantum transfer learning architecture, as it is basically meant for binary classification tests. For experimenting the performance analysis, we varied the quantum depth level of bare variational circuit by 248 units to observe the corresponding behavior of the model in terms of accuracy and loss. As we can refer from the table, the accuracy and the loss of the model varies according to the variation in the quantum depth. After studying the table, we can conclude that at quantum depth 4, the output obtained in terms of accuracy and loss is optimum. And as compared to other models, that is ResNet 50 and exception model, the quantum transfer learning performs much better.
And that brings us to the end. I would like to thank you for your time and attention today.